Hello, today we're going to talk about the kinetic molecular theory and gas laws. Okay, so let's quickly review kinetic energy. Kinetic energy is the energy of motion, and temperature is a measurement of the average kinetic energy for a sample. So when you have substances at a really high temperature, they're going to have particles that are moving faster, and things that are at a low temperature have things that will be particles that are moving slower. So high temperature is faster motion on average, and lower temperature is slower motion on average. So there are three components to the kinetic molecular theory for gases. The first assumption we can make for kinetic molecular theory is that gas particles are small hard spheres, in constant, rapid, random motion. So we can picture gas particles as these tiny balls that are moving rapidly and randomly throughout their available space. The second assumption that we have for kinetic molecular theory is that the volume of the particles themselves is very small compared to the volume of the container. And so we say that the volume of the particles is negligible. So small that it doesn't matter. And our third assumption for kinetic molecular theory is that when gas particles collide, so collisions, either the particles are colliding with each other or with the walls of their container, their collisions are perfectly elastic. Which for this class, what you need to know is that there's no energy loss to like heat or friction during those collisions. And so those are the three assumptions that are going to help us define the movement and behavior of gases. So now let's talk about gas pressure. Gas pressure arises when you have a container and you have your particles in the container, and those particles are colliding with the walls of the container. And so the particles are exerting a force, and that force is gas pressure. So the collisions with the container creates pressure. And so when you have a vacuum, there's no gas particles. And because there's no particles, there's no pressure. And so there's a number of different things that will affect those collisions with the walls of the container, and that's going to define how gas pressure changes in different scenarios. Now we have gas particles all around us in our atmosphere. And so the force exerted by the particles in the atmosphere is called atmospheric pressure. So let's say we've got our little person here, right? And we're on Earth, and there are particles of air. And air is composed of a lot of different gases, right? Carbon dioxide, oxygen, mostly nitrogen. Nitrogen takes up most of the particles in the air, but there's also like water vapor and trace gases. Those things are colliding with the Earth, with objects, with you. All those collisions are creating that atmospheric pressure. And barometer is the device that we use to measure atmospheric pressure. Atmospheric pressure. And so when we're really close to sea level, we say that it's very close to 1 standard atmosphere. And we call a standard atmosphere an ATM is abbreviated. So a standard atmosphere is abbreviated ATM. Now, if you go to higher altitudes, then you'll have less pressure, or you'll have less than 1 ATM. Because as you go like up a mountain, if you're standing at the top of a mountain, right, or just any really high elevation, you're going to have less air above you that is pushing down and exerting pressure. So higher altitudes have less pressure, lower altitudes have more pressure. And sea level is 1 standard atmosphere. But you can actually get higher than that, depending on what's going on in your surroundings. Now, I just talked about standard atmospheres, and that's one of our pressure units. So we can say 1 standard atmosphere is 1 ATM. But there are other common units of pressure. We also use kPa, and pascals is actually the SI unit of pressure. But kPa is just about 101.3. 101.3 kPa is equal to 1 atmosphere. Sometimes people will estimate that as 101 kPa instead of 101.3, and that's all right. But we also use units called torr, which are, there's 760 torr for 1 ATM. And this is the same thing as 760 millimeters of mercury. So barometers used to have mercury in them, and they would literally measure with like a ruler, a millimeter ruler. And so at 1 atmosphere, the height of the mercury would be 760 millimeters. And so we don't use mercury in our thermometers or barometers anymore because of the hazards involved, but that's where that unit came from. And so these are just different units. You'll also see things like PSI, pounds per square inch, but that would not be a metric measurement. Now, when we're talking about gases, we also use something called STP, standard temperature and pressure. Now, standard temperature for gases is going to be 0 degrees Celsius, which is equivalent to 273 Kelvin. Now, you can go into more detail and get it to 273.15 Kelvin, but it's okay. For this class, I'm okay with you using 0 degrees Celsius, 273 Kelvin. So all of our experiments at STP are going to be using this temperature. And it's just a way to standardize our experiments. Standard pressure then is 1 ATM, or we could say that's 101.3 kPa, or we could say it's 760 torr, or 760 millimeters of mercury, depending on what unit we're using. And so these are standard temperature and pressure to like make all of our experiments the same across STP. Let's practice converting between different pressure units. Let's say we have 350 kPa, and I want to get it to ATM. I know that 101.3 kPa is the same as 1 ATM. I put the kPa on the bottom so it would cancel. And then to solve that, you would divide 350 divided by 101.3. And you would get 3.5 ATM. And I'm using 2 sig figs here. It's actually a 3.455, but when you round to 2 sig figs, you get 3.5. Let's do another one. Let's say I have 1,050 torr. And then I know that there are 760 torr for 101.3 kPa, because both of those are equal to 1 standard atmosphere. So what I would do for this one is I would multiply by 101.3 and divide by 760. I need to do both of those things. So times 101.3 and divided by 760, and I get 140 kPa. And I put the decimal there to show that there's 3 significant digits, just like the 3 sig figs in my problem. Okay, now we're going to start talking about the gas laws. There are many things that affect gas pressure. We're going to focus on 3 of them. V, which stands for volume. So the volume available for the gases to move around in. T stands for temperature. So the average kinetic energy that the gas particles have temperature. And then N stands for the moles of gas, which for our class, we're going to figure out that this has to do with the number of gas particles. Okay, so a larger number of moles of gas means you have more particles moving around. A smaller moles of gas, you have fewer particles. Now, how do these things affect the gas pressure? Let's talk about volume first. Volume is the space it has available to move around in. And so this first box has less volume and the second box has more volume. Okay. Now, if I have 3 particles in there, the 3 particles in the smaller container will have more collisions because there's less space. The 3 particles in the larger volume will have less collisions with the walls of the container because there's more space to move around, so it's not going to bump into as much. So because of that, when you have more collisions, that's going to make it have a higher pressure. When you have fewer collisions, you will have less pressure because there's less force exerted by those particles on the walls of the container. Now let's talk about temperature. Temperature, let's assume that we've got our 2 containers are identical. We have the same number of particles. But at a high temperature, they're moving faster. At a low temperature, they're moving slower. If they're moving faster, they're going to collide with the walls of the container more frequently and with greater force because they have more energy, more kinetic energy. At a lower temperature, they're going to collide less frequently, and with less force, they have less kinetic energy. So at higher temperature, they're going to have higher pressure, and at lower temperature, they're going to have lower pressure. Now for our third one, for our moles of gas, again, I'm going to use 2 of the same size container. Okay. Let's say I've got 3 particles in the first container, but I've got 6 particles in the second container. Okay, let me see if I can actually draw this a little bit more so you can tell that they're the same size container. Okay. The more particles you have, the more collisions are going to happen because there's more things to collide. Fewer particles will have less collisions. So this will have more moles. This one, I'm sorry, I wrote that backwards. This one will have less moles. This one has more moles. And so fewer moles means you're going to have less pressure. More moles means you're going to have more pressure. And so you need to know those relationships between pressure, volume, and temperature, and moles. Okay, so let's start talking about the combined gas law. The combined gas law relates pressure, volume, and temperature to one another. And for this equation, we need to make sure that temperature is in Kelvin, because Kelvin has no negative numbers, and if we put it in Celsius and there's a negative temperature, it will throw everything off. So it has to be in Kelvin, and that's how it's related properly. And so the actual equation, which you should be familiar with, is the pressure and the volume and the temperature. Temperature is on the bottom. So I say P1 V1 over T1 is equal to P2 V2 over T2. And we can assume that like 1 is for your initial conditions and 2 is for your final conditions. Or you can just say your first set of values versus your second set of values. And we can plug in our pressures, our volume, and our temperatures into this equation to get to be able to solve for one that is unknown. Now, the great thing about this is that if your temperature is constant, you can ignore it from the equation. So if temperature is constant, I would just get P1 V1 equals P2 V2. Or if pressure is constant, I can get V1 over T1 equals V2 over T2. And if volume is constant, I can get P1 over T1 equals P2 over T2. So we wind up really having 4 gas laws here, but you can get away with just knowing this one and like covering up the one value that is constant. And so we're going to do a couple examples of this. Okay, so this one, what is the new pressure of a gas originally at 2.45 atm if its volume increases from 4.5 liters to 6.8 liters? So the combined gas law Now, it doesn't mention temperature anywhere. Because of that, we can assume that the temperature stays the same. Sometimes it will even say, like, if the temperature is constant. But it's not mentioned here, so we can just ignore temperature from the equation. And now we say the gas was originally at 2.45 atm, so that's our first pressure. And it says the volume increases from 4.5 to 6.8. So our first volume was 4.5 liters. And our new volume is 6.8 liters. We don't know the new pressure. That's what we need to solve for. And so what I'm going to do is multiply this side. And so I get 11.025 equals P2 times 6.8, and then to divide 6.8 from both sides. And I get 1.6 atm is my new pressure. And I used two significant figures here because there was two in my problem. This one has 3, but that's too many. The 2 would weigh out for your final answer. Let's try another one. So temperature of 1.5 liters of gas increases from 52 Celsius to 95 Celsius. What's the new volume? Uh-oh, it's in Celsius. We said that it has to be in Kelvin for the combined gas law. So for both of those, I'm going to add 273 to get the Kelvin temperature. So we'll say 325 Kelvin for this one. And when you add, you get 368 Kelvin for this one. Now that I have Kelvin temperatures, I can use the combined gas law. P1V1 over T1 equals P2V2 over T2. And we've got a volume here, liters, and temperature, but there's no pressures. So we can assume that the pressure stays the constant, and I can just use volume and temperature. We've got 1.5 liters to begin with, and our original temperature was 325 in Kelvin. I need to find my new volume when my temperature changes to 368 Kelvin. Easiest way I think to solve this is to cross multiply. So 1.5 times 368, says 552 is equal to 325 V. And to get V by itself, I divide both sides by 325. And with 2 sig figs, I get that my volume is 1.7 liters is my new volume. Our last example here, if the volume of gas at STP is 450 milliliters, what is the new volume if the pressure is 1.5 atm and the temperature is 24 degrees Celsius? Uh-oh, degrees Celsius. I need to change that to Kelvin. So add 273. I get 297 Kelvin. Okay, and so I've got P1V1 over T1 equals P2V2 over T2. So if the volume of a gas at STP is 450 milliliters, so STP tells us the temperature and the pressure. Standard pressure is 1 atm. They tell us the volume is 450 milliliters. And our original temperature is STP, which means it's 273 Kelvin to begin with. The new pressure, they told us, was 1.45 atm. We don't know the new volume. And the new temperature is 297 Kelvin. Now, I want to solve for V2, so I'm going to cross multiply. Let's go this way first. 1 times 450 times 297 gives us a really large number. And then the other way, when we cross multiply, 273 times 1.45, we get 395.85 V. And then to get V by itself, you divide both sides by 395.85. And when you solve and you get 2 significant figures, you get 340 milliliters is your new volume. It's like 337.6, rounded to 2 sig figs. So our last topic for this section of notes is on ideal gases. An ideal gas makes a couple assumptions that makes it very easy for us to predict the properties of that gas: pressure, volume, moles, temperature. So those assumptions for an ideal gas is that there is no volume for the particles themselves, for the gas particles. Not the volume of the container, but the actual space that the individual particles take up, is that there's no volume. Okay. We also assume that an ideal gas has no attractions between the particles of a gas. Now, this is an idealized version of gas particles. It does not exist in real life. Real gases, they do have a volume of their particles that takes up some of the space in their container. They do have attractions between their particles. So what we can do to get to a situation where a real gas is going to behave more like an ideal gas. A real gas, if we have very small gases, so if they're really tiny gases like helium gas or hydrogen gas, very small ones are going to behave more ideally. And also gases that have minimal attractions. Minimal. And so usually these things are like nonpolar gases. Again, hydrogen, helium, neon is a good example. Nitrogen is pretty minimal in terms of attractions as well. And then we can also make it behave more like an ideal gas at very high temperatures, because when they're moving faster, they're less likely to form those attractions between their particles. And if we have very low pressures means that they're going to be more spread out and form less attractions between the particles. It also means, because they're more spread out, that the volume of the individual particles is going to make less of an effect. So high temperatures, low pressures, and then if the smaller they are and the fewer attractions they have, the more it behaves like an ideal gas. Now, so we've got something called the ideal gas law, and the ideal gas law is PV equals nRT. And so this relationship between pressure, volume, moles, a gas constant, and temperature holds true for ideal gases. Right? We talked about how ideal gases have no volume for their particles and no attractions, and we talked about a few ways that we can get real gases to behave more ideally. And by behaving more ideally, this equation is more valid. So let's break it down. P is pressure. And for the ideal gas law, I want you to make sure that pressure is an ATM. For V is volume. And for the ideal gas law, I want you to make sure that the volume is in liters. N is moles, which is the unit. It's the number of particles. T is temperature. And temperature must be in Kelvin, just like the combined gas law, must be in Kelvin. And then we have this R. R is called the ideal gas constant. And for this class, as long as you're using ATM, liters, moles, and Kelvin, then your constant is 0.0821. That's for 3 significant figures. And so every time for this class, every time you plug in to the ideal gas law, you're going to use 0.0821 for R every time. So that's why it's called a constant, because you're going to use that value every single time. So let's do a couple of examples with the ideal gas law. How many moles are in a sample of a gas at 300 Kelvin if it has a pressure of 1.45 atm and a volume of 4.78 liters? So our equation, PV equals nRT. Pressure, they told us, was 1.45 atm. Volume is 4.78 liters. We don't know N, that's what we're looking for. R is the gas constant. It is a constant, so you're going to always plug in 0.0821. And our temperature in Kelvin is 300. So let me simplify both sides. So when I simplify this side, I get 6.931. And then when I simplify this side, I get 24.63 N. And to get N by itself, I'm going to divide both sides by 24.63. And when I do divide there, I get 0.281 is N. But our temperature here is only 1 sig fig. So when I round that to 1 sig fig, I get 0.3 moles is our value for N. So this one is our last example for today. We're going to be looking for the pressure of the gas, and they give us this many moles, a volume, this one's in milliliters, and a temperature that's in Celsius. I need to change some units here. So when I have milliliters, I need to change that to liters. It must be in liters for PivNert. So 785 milliliters. There are 1,000 milliliters in 1 liter. So 0.785 liters. I also need to change Celsius to Kelvin. So add 273. I get 338 Kelvin. Now I can use PivNert, PV equals nRT. Pressure is what we're looking for. Volume in liters is 0.785. I have 0.573 moles. Gas constant is always the same, 0.0821, and temperature in Kelvin is 338. I'm going to multiply this side. I get pressure times 0.785 equals 15.9, and to get pressure by itself, I'm going to divide both sides by 0.785. And I get 20.26, but that's ATM. Now, the question wants us in torr, so I need to convert this to torr. 20.26 ATM. I know that for every 1 ATM, there's 760 torr. So ATM cancels, and I just need to multiply by 760. So I get 15,394 torr, but I need to round using sig figs. And it looks like I have 3 significant digits here, because when I get to temperature, it's 3, 3, 3. I need to use my final because you're adding there. So to 3 significant figures, that would be 15400 torr is my final answer.